Live from my basement, a little bit of math. Descriptive statistics. So there are three types of descriptive statistics we'll look at in the next week or so. Measures of center, measures of spread, and measures of position. So measures of center are things like average, which we also refer to as mean, median, and then mode. And mode is a little bit different than the other two. Mode is the most frequently occurring. And sometimes there isn't a mode. Sometimes it doesn't make sense to have a mode. The way I think about mode is more useful for qualitative data. So for example, color. I like black and white and purple and green. And if I looked in my closet at my shirts, I have some black shirts and some white shirts and some purple shirts and some green shirts. And it wouldn't make sense to find the average color of my t-shirts. It doesn't make sense to find average gender, right? You can't add up male, 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 female, female, and divide by how many. It doesn't make sense. Those are words, not numbers. But there is a more frequently occurring color in my t-shirts, and there is a more frequently occurring gender in most groups. So mode is kind of a measure of center for qualitative data, but we also use it for quantitative data sometimes too, and we'll see some examples of that. Mean is add them up, divide by 2. Another way to think about mean is if you were sharing. If you took what everybody had and evenly distributed it, then everybody would have average. Median is whatever number's in the middle when we put the numbers in order, and we'll look at some examples of that with two different data sets in a moment. Measures of spread. So there's an idea of range, and that is the distance from the smallest to the largest number. So the maximum minus the minimum. And there's a measure of average spread called standard deviation that we'll spend a bit of time on. And again, standard deviation is a measure of average spread from the mean. So that's a very important one to play around with. And then measures of position. So measures of position are, there's a first number, the minimum. Then we break the data into quarters, and each place you slice to say, hey, this is the first 25% of the data is a quartile. And so there's a first quartile. And then the median is exactly in the middle. So it could also be considered the second quartile. And then there's the third quartile. And then there's the max. And these 5 numbers essentially split our data into 4 groups. So between the min and the first quartile is the first quarter of data. So 25% of the data lives within those in between, including the min and the quartile sometimes. And 25% of the data lives in between the first quartile and the median, and another 25% of the data lives between the third quartile and the max, and another between the median and the third quartile, and then 25% between the quartile and the max. And we'll envision this 5-number summary here by drawing a box plot. And so that'll be near the end here. Box plot. So those are the main topics we're looking at this week. So let's get started. Here I have a summary of a data set. There was a survey of 361 students. So a sample size is a statistic. And a statistic is something we calculate based on a sample. So calculation based on a sample is called a statistic. So here I have a bunch of different statistics. Sample size is one of them. Often we give that the letter N. Mean or average, we usually give letter X with a bar over the top. So the average, in this case, it would be number of TV hours per week a student watches from this 361 group of students. So we can see some students watched a lot and some students watched very little. Standard deviation, that's usually given the letter S for standard deviation, and that's the sample standard deviation, which is different from a population standard deviation slightly. Minimum, no real special letter or anything there. We'll usually abbreviate that with min. Similarly, maximum is max. Q3 is the third quartile. Q1 is the first quartile. So this program I'm using here, StatKey, which I have linked in the course, has data you can select from and take a look at, and they give you some summary statistics. So usually they display a dot plot. I asked for a histogram, and then I selected the number of buckets for that histogram. I have 8 buckets from 0 to 40, so that means they go from 0 to 5 and 5 to 10 and so on. So you can see this data set, most students watch very little TV. So majority of students live over here, watching somewhere between 0 and 15 hours of TV. And there's a few students that live out here on the fringes, watch way more TV than they should. Maybe they do that and do well at school. I don't have that data. All I know is how much TV they watched. And I can change the number of buckets, play around. We experimented with histograms last week, but they're a powerful tool. StatKey also has a box plot generator, which is nice, alternative to drawing them by hand. So I'll open up StatKey and then we'll do the similar calculations on a spreadsheet, which is also a nice place to have stuff. So from the StatKey homepage here, I want to go to Descriptive Statistics and Graph, one quantitative variable. And either I can plug in my own data, so I could upload or edit data to do so, or I could look at one of their data sets. And I'm going to choose their TV hours, which is the one I just had. They display a dot plot for it, which just has a dot for each data value. And they have the summary statistics off to the side here, which they nicely calculate for us. And we'll try that in a spreadsheet in a moment. I can choose a histogram. Default buckets is 10, but you could choose to have more. Try a regular mouse. There we go. More buckets or less buckets. And I just liked 8 because it fit well with their numbering scheme at the bottom. Otherwise, the numbering scheme doesn't necessarily match up. Let's say we went for 12 buckets. But if I point to any, the bottom right corner will tell me the boundaries on that bucket. So the one I'm pointing to there has a low of 10 and a high of 13.3, and there were 46 students that watched between 10 and 13.3 hours of television each week. By television, they meant any kind of video type thing. So it could be YouTube, could be Netflix, could be broadcast TV, cable, lots of options there. Too many. But anyway, so into a spreadsheet. So to do that, I'm going to choose, let's try edit data. And then I'm going to just highlight all of their data with my mouse and Control-C, copy it. And I'm going to drop it in here to my Descriptive Statistics page, where I already have some labels for the statistics I want to calculate. And let's just do some statistics. So count is a calculation, and there happens to be a count option. Count the number of numeric data values in a data set. So that's the one I'm going to choose. And since that's the numbers in the label are the only thing in there, I'm safe to just click on the title and say grab everything in column A. If you have any doubts, like there might be some other numbers in there, then instead you would have to click on the first and then drag down, or Control-Shift down arrow. Control-Shift down arrow will find the bottom of the list. And either way, it told me there were 361 numbers. So it turns out it would have been safe for that function to click on the column heading. And every function is a little bit different. For all of these, it is safe. Mean is average, and same thing works in Excel. Average is 6.5, which should match what StatKey told me. Median, data, mode, equals, so we start with equals, and I want mode, not mod, two very different calculations, and again, it gives me a definition when I point to it. Close your parentheses. Interesting, the median and the mode are the same. That doesn't always happen. The reason I'm grouping these in this way, these three numbers here are what are called the measures of center. Right, so they're in this region. Measures, actually, let's move that over a little bit. Now leave it there. Measures of center. And then down here, these I'm going to calculate are measures of position. Not position, excuse me, measures of spread or variability. Sometimes spread is variability. There we go, close enough. And so that would be the min, because I need that to know the range, and the range is information about the spread. So get the min, get the max, and again, read the descriptions if you're not sure which one to grab, and then the range would just be equal to the max minus the min. Standard deviation, there's a bunch of different ones, so I just start by typing ST for standard deviation, and I usually use just the one called STDEV. Another one is the STDEV.S for a sample. Either one is good. I think Excel defaults toward the S.S one, and it should give the same results as the STDEV. So I'm going to go with the basic one. And so that's the measure of average spread from the middle, and we'll take a look at that on the graph in just a sec. And then these down here, this next grouping, these are measures of position. And then you might ask, well, how come some of these are in multiple spots? So again, median is one way of saying, hey, we think this is about the middle. And median makes sense in some places and not in others. So if I were to look at, say, baseball player salaries, professional baseball players, most baseball players make a pretty good salary, and there's a few that make ridiculously huge salaries, and they drag the average higher than what the usual player makes. Median just says, hey, give me the middle, and it doesn't matter whether the maximum is 5 million or 50 million. The median will be the same number in the middle. So the max and min don't really affect the median, whatever their values are. It's just, hey, I'm the number in the middle. Whereas if the max was 5 million versus 50 million, a data set with a max of 5 million will have a higher mean than a data set of a max with 50 million. I said that backwards. 50 million will drag the mean higher. Min and max are listed here under measures of spread / variability because I need them to calculate the range. But they're really measures of position. The first number is the minimum. The last number is the maximum. If there are 101 numbers, then the 51st number will be the number in the middle. Okay? So measures of position. Quartile 1 is the number that you would cut at the data set so that 25% of the data is at that position or lower. And we'll see that on a box plot in a moment. All right. So making those calculations, again, like before, we got min, data, parentheses, quartile is a little trickier. Start typing quartile. And let's see, I believe it's quartile and quartile inclusive are the same one. I'm just going to go for quartile. So then select the data. But then you got to tell it which quartile you want. Do you want the first quartile, the third quartile, or one of the others? And so I'm going to type 1 for first quartile to mark the first quarter. And then median, which we have above, we're just going to repeat for fun. Quartile 2 starts the same, or quartile 3 starts the same way. Start typing quartile, select the one you want, select your data, and now I want the third quartile, so I type 3, and the max. Data done. So it turns out when we break the data into quarters, there are 5 numbers that are significant. And so you could say then there are 5 quartiles. So this one, the min, would be what we call the 0th quartile. And the quartile 1 is obviously the 1st quartile. And then the median is also the 2nd quartile. 3rd quartile marks the place where 3/4 or 75% of the data is at or below. And the 4th quartile would be the place where 4/4 is at or below. So 100% of the data is there or below. That has to be the max. So it turns out I could also find the median by saying, hey, give me a quartile from the data, and I want the 2nd quartile for which 50% of the data is at or below. Notice that's the same number here. So it turns out there are multiple ways to get a median, min or a max. Quartile function is one way, there are others. Okay, so those are the standard summary statistics, and StatKey again gives you most of those. Sample size, which I call the count, mean, standard deviation, min, Q1, median, Q3, and the maximum. Again, StatKey has a nice histogram maker where you can choose the number of buckets you want, fewer or more. You also have a box plot generator, so it looks at the numbers. Now it's doing something a little bit different. It's looking for outliers here, and we'll look at that calculation in another video about why they break off here. There's at least 2 different ways to make a box plot. One is where you make a dot or a mark for the minimum, and then a mark for wherever Q1 is, the median, Q3, and then the max. And you draw a box around quartile 1 to quartile 3, put a line wherever the median goes, somewhere in between, and then draw whiskers from the edge of the box to the min and then out to the max. This system is doing a slightly different approach where it's calculating numbers that seem far from the majority of the group, and they're using a thing called the IQR, interquartile range, and again I'll explain that in another video. So they're making an earlier cutoff than the max, and they're saying, hey, everybody outside of this point right here, like 16-ish, 17-ish, is they watch way more TV than the average, because this box right here is 50% of the students. And then here's another 25%. So 75% of students watch up to, let's see, what is that, 9 hours per week. This right here is not the maximum. The maximum is way out there. Right. So again, a version of a box plot. We'll do a different one in a moment. All right, so let us play around. So histogram, let's go back to the 8 bucket one. Actually, I already have a copy of that, but let's get a new one. All right, come on, there. And I'm gonna screenshot you and play around. And new page, please. All right, so I want to just take a look at here the mean, average, and standard deviation. So we calculated an average value of 6.5-ish and a standard deviation of about 5.6. And let's just, for ease, call it 5.5. So 6.5 and 5.5. So I'm going to make a mark on here for those values. So note at the top here, we have, let's use red, X bar, that's the mean, is approximately 6.5 hours per week. And S, the sample standard deviation, is about 5.5. To get those straight. Yep. So if that's 5, and that's 10, 7.5 would be in the middle there, and then 6.5 would probably be about right here. So that is my x bar, my mean, my 6.5. Standard deviation, again, is a measure of average spread from the mean. And you're going to read the book about how that's calculated. I'm not too worried about the how of it right now. So definitely want you to read about that. But just this is what it is. So if I, from the mean 6.5, measure out 5.5, right? So if I take x bar plus 1 standard deviation, that gives me 6.5 plus 5.5, which is 12. So out here, so 12, let's see, 1, 2, 3, 4. That wasn't very good cuts. Let's try that again. I'm trying to cut this into 5 pieces. How about 1, 2, 3, 4? Oh, pretty close. So I think 12 is about right here-ish. So this is plus 1 standard deviation. I could also go minus 1 standard deviation. So if instead I said, let's find x bar minus 1 standard deviation, that would be 6.5, the mean, minus the standard deviation of 5.5, which leaves me a 1. And 1's going to be right about here. So that would be minus 1 standard deviation from the mean. So that minus 1s is an abbreviation of the mean minus 1 standard deviation. And that plus 1s is a abbreviation of the mean plus 1 standard deviation. Now, it doesn't make sense to go 2 standard deviations to the left because that's negative numbers and you can't watch a negative amount of TV in a week. But we can keep going the other way. So sometimes we run out of space when we're doing calculations, and that's okay. So I could calculate 2 standard deviations to the right. So what would be x bar plus 2 standard deviations? So that would be 6.5 plus 2 times 5.5. So that'd be what, 11, and 6.5 is what, 17.5? Yeah, that looks about right. So that's right, almost exactly in the middle here. So that right there, that 17.5-ish, right between 15 and 20, that would be plus 2 standard deviations. One more time, just for the hell of it, what would be x bar plus 3 standard deviations? Try that again, there we go. So that would be 6.5 plus 3 times 5.5. And just add another 5.5 to that, which gives me 23, I think. So 1, 2, 3, 4, 5. So 23, that would be about right here. So that's plus 3 standard deviations. And what we're going to find for most data sets, if we look between 2 standard deviations of the mean, so the second standard deviation to the left would be somewhere over here in the negative land, minus 2s. So if I look at how many of these students that we looked at have their number of hours are somewhere between whatever that number is and this number right here, we should usually see it's somewhere between 75% and 90% of the data will be in there. And every data set's a little bit different. And usually almost all of the data will be within 3 standard deviations. So if I look back at my data set, so my second standard deviation was 17.5. So show table, and let's put these suckers in order. Data, sort range, has a header row, A to Z. So if we find 17.5, okay, so it goes from 16 to 20, so that would be 16 and below. And we count up these guys. My computer summary on the side here says count. 338 of them are what I just highlighted. So a quick calculation. So I'm trying to count data within 2 standard deviations. I counted 338 out of 361, which gives me, whoa, look at that, 94%. Pretty good. So about 94% of the data is within 2 standard deviations, and that is not uncommon. Just kind of depends on the data set. Everyone's a little bit different. Your book mentions this. Definitely hope you read that. So summary statistics, one thing we do is we use the standard deviation to take a look at if anything is unusual in the data set. And usually there's a rule for 2 standard deviations. If there's a score, a measurement that's more than 2 standard deviations to the right or less than 2 standard deviations to the left, then those numbers are unusual compared to the majority of measurements in the data set. So we would say anyone that watched more than 17.5 hours of TV watches unusually more than the rest of the students. So that's one measure. The box plot that StatKey made gave us another measure. And so when I look at the box plot here, they put the cutoff for unusual right here, which it's about, I thought it was about 16-ish, 16 and a half. So that's saying, yeah, anything above that is unusual. So the 2 standard deviation rule and the box plot rule kind of match here. And I'll look at another example of that in a moment. Next thing I want to do is I want to line up the box plot with the histogram just to get a feel for the spread of the data. So let's do that. Screenshot. And this part is a little tricky on a computer. It's easier on paper. Let's put that on a new page. And I'm going to shrink you down just a little bit. And I'm going to see if I can put you at the bottom. And we're going to graph the histogram with that. And I'm going to do my best to line these suckers up, get their scales to match. So let's bring you up there. And then we're going to get the 40s to line up. So there's 40 there, and we're going to get the zeros to line up. There's 0 right there. That mostly lines up. And let's squish it a little bit more. That looks reasonable. Okay, so I want the 5, 10, 15, 20, and so on to line up. All right, so StatKey is doing one variation of a box plot. Another variation of the box plot I'll draw above. You make a mark for the min, and then you make another mark for Q1, which is about here-ish, first quartile, and then another one for the median, and another one for the third quartile, which looks to be about here. So all I'm doing is taking these lines on the scale and just drawing them up above, and then the max, which is way the hell out here. And then what we do is we draw a box around Q1 to Q3 to the best of your artistic ability with a line through the median. The dots are optional. Notice StatKey didn't draw them. And then from the box to the min and from the max to the box, you draw lines. Oop. Pen freaked out again. Okay, so this is kind of the standard version, the simple version of a box plot. Here they made a box plot with an extra calculation for outliers. We'll see that in another one. But what should happen is, again, what the box plot shows me is that 25% of the students have numbers between these two values. Another 25% of the students live between these two values. So they're kind of crammed in. Notice I need to have a taller stack to accommodate all those. The next 25% of students lives between the median and the third quartile, and the last 25% of students is really spread out from the third quartile to the max. And every set of data has a different shape. This data set, I would say, is skewed to the right because it has a tail to the right. So skewed right, because that's where the tail is. Some data, it's hard to tell if it's skewed. Some data is symmetric. There's all different kinds of shapes of histograms. And together with the box plot, I can see wherever I have short stacks, I should see a long part of the box plot. And wherever I have tall stacks, I should see a narrow part of the box plot. Okay? And so that's a nice visual representation of how the data is split up. All right, one more data set quick, and then I'll shut up. So let's go. Come here. We're going to make the same calculations I made in descriptive statistics, but I'm going to make them for a new data set here. So here I have body temperatures from a bunch of mostly college students, some high school students. And I'm going to do a count on that. And the median, which is average, median, MED for median, IAN, and mode. And sometimes mode is useless. Notice I haven't really talked about it here. It's not all that meaningful. Min and max, let's calculate those. So we can get the range. And remember, range is always max minus min. And we have a pretty narrow range, 3.3 degrees, right? That's being human. Standard deviation equals two of them, STDEV, data. And then I already have the min here. No point in recalculating that. And I already have the max here. Oops, wrong one there. And I already have the median up here. So if you ever want to copy another value, type equals first and then click on the value you want to reproduce. Quartile I have to actually calculate. Data, in this case, comma 1 for the first quartile. And remember, quartile is different than a quarter. And I'll repeat that in a sec. And then equals quartile, data, and I want the third quartile, so comma 3. All right, so here are the different values, and it would be nice to see those graphically. So I'm going to also have Google create a histogram, highlight the data, click Give me a chart. Excel does something similar by going to Insert Recommended Charts. Google guessed at a histogram here. Interesting selection. It has a bunch of empty space there for some reason. Wild. But otherwise not bad. I could use a title. Style, where are titles? There we go. So let's say this is a distribution. It's showing how the data is spread out and clumped together of human body temps. Okay. So most of the people that I took their body temperature had a body temperature somewhere between 98 and 98.5. Going a little farther, I could say most of them were between 97.5 and 99. So we'll play around with this in just a second. Actually, let's make a copy of you and draw on it. In StatKey, remember, we'll do a similar thing, so I'll show you how to get data into StatKey. All right, so here's my distribution, and then I want to draw on this my mean and standard deviation again. So the mean is about 98.4, standard deviation is about 0.7, so 98.4 and 0.7. So I'll just make a note. X bar is 98.4 for this group, and sample standard deviation is about 0.7. So I want to just make a mark on my table where that number is. So 98, 98.5, 98.4 probably is about right there. That's my X bar. And then I want to look, one standard deviation to the right, one to the left. So I need to make some calculations. I think I'll have my spreadsheet do that, although that's not too bad right here. So make a little table on the side. Whoa, my pen freaked out there. So let's put here number of standard deviations, and let's go 2 to the left and 1 to the left and 1 to the right and 2 to the right. So like for example, this one right here would be x bar plus 1 standard deviation. So 98.4 plus 0.7 is going to give me 99.1. And then if I add another 0.7 to that, that would be 99.8. Going the other way, if I subtract 0.7 from 94, that's going to give me 97.7 and then 97. I subtract 0.7 again, so that would be 2 standard deviations. So just double check. This number right here is x bar minus 2 standard deviations. So 98.4 minus 2 times 0.7. So that should equal 98.4 minus 1.4, which, yep, 97 looks right. So marking those off here, 99.1 should be about here-ish. So that's what I called plus 1s before. And then 99.8, that's 0.5, 6, 7, 8 is probably about right here-ish. Plus 2 standard deviations. So this distance from here to here is a measure of 1 standard deviation. And then the distance from here to here is another 1 standard deviation. That's what I'm trying to measure out. Going 1 to the left puts us at 97.7. So 5, 6, 7, probably about here. So that'd be minus 1 standard deviation. And then minus 2 standard deviations is right here exactly. Minus 2s. So all of these spaces between the arrows should be about the same. That should be an s, and in this case, s is about 7/10. So how much of my data lives between 2 standard deviations? And this is a relatively symmetric curve, almost bell-shaped, slight tail to the left, which is kind of interesting. Usually the tail drags the mean away from the median, so I would expect the mean to be less than the median here. Is that true in my spreadsheet? Spreadsheet, where'd you go? There you are. Mean is slightly more than the median. Interesting. Okay. Defied my expectation. Every data set's different. Show desktop, please. There we go. So from 97 to 99.8, we could take a look at the data and see how many of the numbers are in there. So is this data sorted? Doesn't look like it. So let's sort column A, sort range, and I want to go from 97 up to, oops, where'd you go? 99.8. All right, so let's count that. So from 97, I want to go to 99.8. And that is almost everybody. So computer counts that at 96 out of 100. So 96% of my data, oops, button, is within 2 standard deviations. So 96% of these temps are within 2 standard deviations. All right, so the book made a claim that at least 75% of the data should be within 2 standard deviations. That comes from a thing called Chebysheva's rule, which we don't need to remember his name, but it's a common estimate in statistics. So those are the basics of descriptive statistics. Oh, I said I'd show you one last thing. Suppose I wanted to do all this in StatKey instead. because StatKey, without having to type all of these commands, gives me most of these numbers. Highlight your data. So from the top, Control-Shift down arrow, Control-C to copy, and then go to StatKey. And in StatKey, you want to be in the one quantitative variable section, and then just whatever data set they give you, who cares, click Edit, highlight and delete everything in their list, and then Control-V, paste in your data. Now my data did not have a header row, so I'm going to undo header, and it didn't have a first column with like names, like this was Gary, and that was Sue, and that was Ruby, and that was Jenna, and so on. Just there's no header and there's no identifier in front of each one. So be careful to uncheck those if it applies, and then hit OK. And StatKey will whip all this stuff out for you. So there's a histogram, and sample size is 100, mean is 98.43, median is 98.4, right? Same numbers StatKey gave me. The max is 99.8, Q1 is 98.05, and if I look back at Q1 here, Q1 is 98.075, so they used a slightly different method for finding that, and that's okay. This is a sticky point in statistics. Quartiles are percentiles, and a percentile is a number in the data set for which some percent is there at that point or below. And it turns out there's different techniques. So a TI-84 calculator does it different than a spreadsheet. There's a different way to do it by hand, and apparently StatKey and Google Sheets do not agree on those numbers exactly. So this may come up in the homework depending on the tool you use. Usually I have quartiles and percentile homework set up so that it accepts multiple of the different techniques for calculating percentiles. StatKey also draws the picture of the box plot, which is nice. And in this case, 2 of the people I measured were unusually low in body temp compared to the rest of the crew. As far as the standard deviation rule goes, back here in my picture, let's see, the second standard deviation caught the maximum number in my data set, so there was nobody unusually had an unusually high temperature, but there were a couple people here, anybody below 97. The 2 standard deviation rule says, hey, they're outliers. They're unusually low because they're on the low end compared to the majority of the group. And again, 96% of people had temperatures within 2 standard deviations of their peers. So what we're trying to do is take data, and 100 numbers is not a lot, but I cannot look at this list of numbers and make sense of it to you. You know, I can say, hey, it looks like there's a lot of 98.4s. And so these summary statistics are used to try and describe the data set, maybe compare it to another data set, and maybe compare it to the population. So for example, what I can say is if this was a good random sample, which we'll talk about soon, what a good random sample is, between quartile 1 and quartile 3 is 50% of the people. So 50% of people should have a temperature between 98.1-ish and 98.9. And there is some evidence that human body temperature is on average a little lower than 98.6, which is what we usually call it. So this box right here, those 2 rectangles together, form the middle 50% of people. Okay. So between the graphs and the calculations we do, we're trying to summarize and describe to somebody aspects of the data. More later. Take care. Bye-bye.